Imagine being able to detect the tiniest change in gravity, the faintest magnetic field from a single neuron firing inside the human brain, or even the subtle presence of a hidden submarine deep beneath the ocean's surface. Imagine seeing what no microscope can see, sensing what no radar can detect, all not through magic, but through the strange and powerful principles of quantum physics. This is the world of quantum sensors, devices so sensitive that they redefining what it means to measure reality itself. We live in an age where precision defines progress. Our GPS satellites tell us where we are to within a few meters. MRI machines reveal the structures of our bodies with astonishing clarity. Seismographs record the trembling of the Earth, and atomic clocks mark time with near perfection. But even these remarkable tools have limits, boundaries set by the rules of classical physics. Beyond those limits lies a new frontier, where measurements are no longer constrained by noise, interference, or uncertainty in the traditional sense. It's a world ruled by the laws of the quantum. Strange, unintuitive, but immensely powerful. At the heart of quantum sensing lies a simple but profound idea. The universe itself, at its smallest scales, behaves in ways that are fundamentally different from our everyday world. Quantum sensors exploit those behaviors, superposition, entanglement, and coherence, to measure the tiniest changes in the environment with unbelievable precision. In the classical world, measuring means interacting, and interacting means disturbing. But in the quantum world, we can make nature reveal its secrets in ways that almost defy logic. Think about an atom, a tiny bundle of energy and probability. Atoms are exquisitely sensitive to their surroundings. A small magnetic field can shift their energy levels. A slight acceleration can alter their wave function. By observing how an atom's properties change, scientists can infer with extreme precision what's happening in the outside world. You could say atoms make the perfect sensors, the most accurate instruments nature ever created. Quantum sensors use these atomic properties to measure time, gravity, motion, or magnetic fields with staggering accuracy. They rely on three strange quantum powers. The first is superposition, the ability of a quantum particle to exist in multiple states at once. Imagine flipping a coin that's both heads and tails simultaneously until you look at it. That's what superposition is, and it allows quantum sensors to probe multiple possibilities at the same time, dramatically increasing their sensitivity. The second power is entanglement. When two particles are entangled, their states become linked, no matter how far apart they are. A change in one instantly affects the other. By using entangled particles, scientists can cancel out noise and amplify meaningful signals in their measurements. The third power is quantum coherence, the fragile synchronization of quantum states over time. The longer coherence is maintained, the more precisely you can measure time or frequency. That SE, why atomic clocks, the ultimate quantum sensors, can stay accurate to within 1 second over the entire age of the universe. Take the quantum clock, for example. These are not ordinary timekeepers. They use lasers to trap and manipulate thousands of atoms in what's called an optical lattice. Each tick of this clock comes from the oscillation of an electron jumping between energy levels inside an atom. These oscillations are so consistent, so pure, that scientists can detect the slowing down of time caused by gravity over just a 1 centimeter height difference. In other words, a quantum clock can tell that time runs slightly slower at your feet than at your head, a direct consequence of Einstein's theory of relativity. Networks of such clocks could one day map gravitational variations across the Earth, improving GPS accuracy 1,000-fold and revealing geological structures hidden deep below. Then there are quantum gravimeters, instruments that weigh the Earth without touching it. They work by cooling atoms to near absolute zero, turning them into matter waves, and then letting them fall freely. As they fall, lasers measure how gravity changes their quantum phase. The result is a map of gravity so detailed that scientists can detect underground voids, water tables, or buried tunnels, all without digging a single inch. Quantum gravimeters could help archaeologists uncover lost cities, help engineers monitor volcanic activity, or even detect submarines by their gravitational signature. Quantum magnetometers are another marvel. Your brain generates tiny magnetic fields whenever neurons fire, but these signals are unimaginably weak, billions of times weaker than Earth's own magnetic field. Traditional instruments can't pick them up, but quantum sensors can. Some of the most advanced versions use nitrogen vacancy centers in diamond. Defects in the diamond crystal, where one carbon atom is replaced by a nitrogen atom, leaving an empty spot next to it. This defect acts like a quantum trap. When scientists shine a laser on it and apply microwaves, they can read out the spin state of electrons inside the diamond, revealing the surrounding magnetic field with extreme precision. Using this method, researchers can detect the faint magnetic whisper of individual neurons. In the near future, we might have non-invasive brain scanners capable of mapping brain activity at the level of single cells, giving us an entirely new window into human thought and consciousness. Now imagine navigating the world without GPS. That's the goal of quantum accelerometers and gyroscopes. Instead of relying on satellite signals, they track motion by measuring how atomic wave functions shift as they move. Essentially, they count the tiniest changes in quantum phase to determine acceleration and direction. Combined, these quantum devices can tell you exactly where you are, even if you're deep underwater, inside a building, or in outer space where GPS signals can't reach. Militaries, submarines, and spacecraft could soon navigate using pure quantum sensing. No satellites, no signals, just physics. The fascinating part is how small these sensors are becoming. Once they needed entire rooms of equipment, vacuum chambers, and cryogenic systems. But now, thanks to advances in laser cooling, microfabrication, and photonic chips, scientists are shrinking them to the size of a fingertip. Some prototypes fit on a single silicon chip, making it possible to integrate quantum sensors into handheld devices. Imagine a future smartphone that can measure gravitational anomalies, magnetic fields, or even your own brain activity, all using tiny quantum chips. That's not far away. The fusion of quantum sensing and microelectronics could turn our everyday gadgets into scientific instruments of unimaginable capability. But none of this comes easily. Quantum systems are incredibly fragile. Any interaction with the outside world, a stray photon, a tiny vibration, even a bit of heat, can collapse their delicate quantum states, a phenomenon known as decoherence. To prevent that, quantum sensors often operate in vacuum chambers, shielded environments, or at near-zero temperatures. Keeping coherence alive long enough to make precise measurements is one of the greatest engineering challenges in modern science. Yet every year, researchers are extending coherence times and improving sensitivity. Step by step, the quantum world is becoming more controllable, more practical, more useful. The real-world implications of this technology are profound. In healthcare, quantum sensors could detect diseases at their earliest stages by identifying the magnetic fingerprints of cancer cells or metabolic changes in tissue. In geology and civil engineering, they could map underground water reserves, fault lines, and sinkholes before disasters strike. In climate science, they could monitor changes in Earth's gravitational field caused by melting ice caps or shifting ocean currents, giving us real-time data on the health of our planet. In defense, they could reveal hidden submarines, detect stealth aircraft, or locate underground facilities. And in space exploration, they could help spacecraft navigate autonomously, far beyond the reach of Earth's signals. Quantum sensing doesn't just enhance our technology, it expands our perception. Combine these sensors with artificial intelligence and quantum computers, and you have systems that can interpret the faintest whispers of the universe in real time. Quantum sensors collect data at a scale of atoms. AI analyzes patterns beyond human understanding. Quantum computers simulate the underlying physics. Together, they form a feedback loop of knowledge, allowing us to perceive the universe in a completely new way. In 2020, researchers achieved something extraordinary. They used a quantum sensor to detect the magnetic field of a single proton, the nucleus of a hydrogen atom. To put that in perspective is like detecting the heartbeat of a fly from thousands of kilometers away. That's how sensitive quantum sensors have become. We're approaching an era where we can measure almost everything, from the quantum foam of space-time to the tiny electrical signals of life itself. There's something deeply poetic about this transformation. Humanity began its journey with crude tools, sticks, stones, and simple curiosity. We built telescopes to see the stars and microscopes to see the cell. Now, with quantum sensors, we are extending our senses into the very fabric of reality. These devices allow us to detect the undetectable, to feel the invisible, to measure the immeasurable. In a sense, they are the next step in our evolution, not of our bodies, but of our awareness. As we develop quantum sensors capable of observing reality at unimaginable precision, the line between observer and observed begins to blur. We start to realize that measurement isn't just about numbers. It's about connection. Every quantum measurement entangles us, however slightly, with the universe we are trying to understand. And maybe that is the ultimate message hidden inside the mathematics of quantum sensing, that we are not separate from the world we study. We are part of it. So, the next time you hear the phrase cutting-edge technology, remember that the true edge is ENT made of steel or silicon, S made of quantum waves, entangled particles, and atoms dancing in superposition. We are entering an era where sensors no longer just detect the world. They decode it. From the depths of the brain to the farthest reaches of space, quantum sensors are revealing the hidden symphony of existence. And as our ability to measure becomes infinitely precise, we may finally understand that the boundary between us and the universe was never really there. This is Beyond Newton, where we explore the unseen world shaping our future. If this journey into quantum sensing amazed you, make sure to subscribe, because the quantum frontier has only just begun.